So, this is 205 216. This lecture is number 10, section 450. Today's Thursday, the 8th day of February. It's today's during the cassette fair, so we're teaching online. The time is 10:30 in the morning until 12 at noon. Uh, can anyone hear me? If you can hear me, could you give me a feedback, please? Pumipat.
Yes, I can clearly hear you.
Okay, thank you. So last time, we talked about some properties of systems. We started with linearity. The linearity property of systems is that if we have a system T, okay, and the output of the system T to the input x1, suppose it is y1, and if we uh, have the input x2 to the system T and the output is y2, then if the system T is linear, we're going to have, if we have a linear combination between x1 and x2, this is called a linear combination. The output would be the linear combination of y1 and y2 as well. So basically, you can take the operator t, which is the system, inside of the parentheses, all right, to get this. Okay, so this is called the linear property of a system. The second property that we talked about last time was the time invariant property.
อาจารย์ครับ
Yes?
อันนี้อาจารย์จะคอร์ดไว้ให้ไหมครับ
Yeah.
โอเคครับ
So the second property is called time invariant. If we have y, if the input x to the system t results in the output signal y, then if we shift the input to any particular time t0, the output to the system, the same system, would be the same output shifted by the same amount of time. So basically, if a system is time invariant, then its characteristic doesn't change with time. Um, the the output to any input would be the same, exactly the same, except that the output is shifted inconsistent with the shifting of the input. So for example, if we have the system T, and if we are inputting a unit step signal to the system T, okay, if the unit step signal is injected into the system T, and suppose that the response from the system T is an exponential signal. Okay, suppose it's like this. Suppose this is the response to the unit step signal of this system. Then If we shift the unit step signal to any particular time, if we shift the unit step signal to any particular time, like that, this is time t0. We shift it. The result would also be shifted, and the output signal is exactly the same, okay, except that it is shifted. Just as the input signal is shifted, the output is also shifted by the same amount that we shift the input signal. So if your system has this property for any input and any uh, shift t0, then your system will be called the time invariant system. Okay, for all t0. All right. So basically, this means the characteristic how the system, well, how the system responds to uh, to the input signal, to any input signal, how the system responds to any input signal, system, well, is the same. Okay, regardless of when the input is applied. Right, so characteristic the characteristic of the system doesn't change with time, is invariant to time change. Invariant means doesn't change. Okay, all right. Now, this was the last time. This is how we ended last time. If you have any question, all right, feel free to ask anytime. But if you don't, we're gonna move on to the next property. Okay. So the next property is memoryless. A system is called memoryless or instantaneous if the output of that system at any time depends on the value of the input at that same time. All right, the output of the system the value of the output doesn't depend on the future input, doesn't depend on the past input. It just depends on the present input. The value of the present input, only that value, only the value of the present input can affect the value of the present output, not the past, not the future input. If your system has this property, then your system will be called memoryless, a memoryless system. So if its output at time t0 depends, the keyword is only, depends only on the value of the input at the same time. So t0 here and t0 here are the same time. All right. The output signal doesn't depend on the past or the future values of the input signals. So, for example, an ideal resistor, if you have an ideal resistor, right, then this equation is true. The voltage across the resistor is proportional to the current. The voltage is proportional to the current through the resistor at any time. You see, the key here is they are at the same time. The voltage at the present doesn't depend on the current in the past, nor the current in the future. It only depends on the present current as well. So, and R, the value of R doesn't change with time because it's an ideal resistor, all right? The value of R is constant across all the time, constant over time. So, an ideal resistor is a memoryless system because the output doesn't depend on the past, the output doesn't depend on the future, it just depends on the current value of the current. Another system is a capacitor. We know from circuit theory that if we have a capacitor C, okay, if you have a capacitor C and we measure the value of the voltage across this capacitor and call it Vc, the capacitance is C, and if we have a current that goes into the capacitor and call it IC, then we know from circuit theory that IC is the first derivative of Vc by dt multiplied by the capacitance C. So from this differential equation, we can solve for the voltage across the capacitor, which is Vc, and it is 1 over C, the integral of the current through the capacitor up to time t. And if we regard the voltage Vc as the output, then we see that the value of the output at time t depends on the value of the input at time prior to t. All right, because we are integrating from the past until the present. All right, so Vc depends on the past values of IC. So from this integral, from here, from this integral, we see that the present value of Vc depends on the past values of IC. Therefore, this capacitor is not memoryless. They are not memoryless devices because they have memories, right? They have memories. Okay, so to be memoryless, the output has to depend on the present input only. The next concept of systems is called causal systems. A system is called causal if the output signal, if the present value of the output depends on the past or present. The present value of the output signal does not depend on the future input signals. Okay, it depends. It can only depend on the present and the past values of the input. It doesn't. The present value of the output does not depend on the future values of the input. cannot. Think about it. You haven't applied the input yet. How come the output changes? Okay, if you haven't applied the input yet, right? Because if the system is not causal, then if the system is not causal, then the present output depends on the future input somewhere in the future, right? And that's not really realistic, isn't it? Because you haven't yet applied the input. How come the output changes? Okay, so causal systems are quite realistic systems, but you see, there are systems in electrical engineering that are not causal. Okay, and you may wonder why systems are not causal. Uh, you see, certain systems are implemented, okay, using computers, using memories, so you can record the future values of the input into a memory system, and then your system takes the input, takes the future values of the input into the systems. So if your system is digital, then it may be possible that you can construct systems that are non-causal. But if your system is analog without any memory at all, then you cannot have causal. You only have causal systems. You cannot have non-causal systems. If you don't have memories, if you're not, if you if your system is not digital, okay, you cannot have non-causal. You can only have causal. So the note is that memoryless systems are always causal. Okay, because memoryless systems, the value of the output of the memoryless system depends on the present value of the input, doesn't depend on the future value of the input. So memory systems are always causal, but not the other way around. So if you have memory system like this, then causal is bigger. Okay, this is causal. This is memoryless. Memoryless systems are subsets of causal systems. Okay. Now, in this example, you see the value of your output at time t depends on the past values of the input, right? Does not depend on the future value of the input. So in this example, the system is causal because the output signal depends only on the past values, not the future values. All right. But if instead we have yt equal to integral from minus infinity to t plus 1, what I did was I added 1 to t here. So you see, the present value of the output depends on the future value of the input, right? Because if you want to find the output at time 0, then you have to integrate the input up to time 1, and that would be the future time. So the system defined by this integral will not be causal. Okay, because the output at time t depends on the value of the input from time t to time t plus 1. Because the value of y at time t depends on the values of the input from time t to t plus 1, which are in the future. Okay, this one is causal, but this one is not. Okay, another example, you see the value, the system, this system is defined by y equal to xt plus xt minus 1. So the present value of the output at any time t depends on the present value of the input plus the past one time unit before. Okay, one time unit before time t. So this is the past value, one time unit before. It is in the past, right? This is the present. This is the present. So this is the present value of the output. This is the present as well of the input. And this is the past value of the input. So you see the present value of the output does not depend on the future value of the input. So this system is causal. However, if yt is equal to xt plus xt plus 1, so you see the time here is one time unit after time t. So this is the future value. This is one time unit after time t. So this is the future value of the input, right? So you see the present value of the output depends on the future value of the input. So the system defined by this equation will not be causal because it depends on the future value. Okay, so this is the concept of causality. Causality. All right. Next, the concept of invertibility. A system is called invertible if we can uniquely, if you can uniquely determine the input signal given the output signal. If somebody gives you an output signal y and the system is invertible, then you, based on the information from y, you'd be able to determine exactly without ambiguity the value, the input signal x. But if your system is not invertible, then given some signal y, you cannot uniquely determine the signal input, the input signal x, right? So the keyword is uniquely. There exists one and only one, all right? There, for any given output signal y, there is one and only one input signal x for the system to be invertible. So basically what it means is that you have a system 1, right? You have a system 1 and you are applying the input signal x into the system 1 and y is the output, right? And if your system 1, if system 1 is invertible, then you can find another system which is called the inverse of system 1, such that if you apply y, you're going to get x back again uniquely without ambiguity. Okay. For example, your system, suppose your system is behaves according to this equation, where your system kind of like reversing your system. What your system does here is reversing the input signal, doing the time reversal of the input signal. Then this system is invertible, because if you know y, if you know the output y, right, you'll be able to determine exactly the input signal x by reverse time by doing time reversal again on the output y. So here, if you have x, right, this is your system. Okay, this is your system, and what your system does is that it's gonna do the time reversal of x, right? So if you're given x of minus t, which is the output from t, then what you do is you do time reverse again. You do time reversal again, after which you're gonna have x back. See, given this, right, you can get x back without any ambiguity. So system t here, defined by this equation, is invertible. Okay, so this is t of x, and this is t of x. Another example is a system defined by this equation where k1 and k2 are constants. Then if you're applying the signal x to this system, your output will be some constant k1 multiplied by x and the result added by k2, right? So if you have x here, and you have your system t, and you have y output here, the question is, can you find another system S such that once y is applied to S, then you get x back? Such system here exists or not? Turns out that the system S here exists because you can define S of y by subtracting k2 from y, right? And then divide the result with k1, and you're gonna get x back. How? Because this is because S of y, right? S of y is equal to 1 over k1 y of t minus k2, but y of t is k1 x of t plus k2. This is y of t, and then you minus k2, and if you do that, you're gonna get x back, right? So this is y. Okay, this is x of y, which is equal to x. Now, another system defined by y equal to x squared. Now, this system is not invertible. To show that a system is not invertible, you can give a counterexample as usual to show that t is not invertible. You can give a counterexample usually. A counterexample is a particular signal, a particular input signal, such that you cannot determine the output, the input, signal back given the information about the output signal. For example, in this example, I am suspecting that the system is not invertible because of the squared here. So I'm gonna give a counter example. So I'm gonna suppose that I know that the output is 4 constant. Then because of how the system here is defined, the input can be -2 or 2, right? It's either one of these. So there is an ambiguity uh, here. So based on y equal to 4, you cannot exactly determine whether the input is -2 or 2. You cannot say because there's an ambiguity here. So this system is not invertible. You cannot find the value of the input. Because it can be either -2 or 2, right? There has to be one. The input has to be one. There has to be only one input, but you cannot find it. Okay, these two can happen. All right, it's either this one or that one to get y equal to 4. So this system is not invertible. To be invertible, the you're gonna have to have a unique uh, signal back here. Okay, you have to be able to determine exactly what x is without ambiguity for the system to be called invertible. All right. Okay. Now the next concept is called Bible stable. Bible means bounded input, bounded output. Now, for a system to be called Bible stable, it has to satisfy the following condition. For any bounded input signal, you're applying any bounded input signal to such system, then the output would have to be bounded as well, right? So, for a Bible bounded input, bounded output, for a Bible stable system, any bounded input has to yield a bounded output. Okay, if you give a system a bounded input, if there is a bounded input signal that results in unbounded output, then your system will not be Bible stable. So mathematically, what it means is that we say that the system T is bounded input, bounded output stable if there exists, well, is for any bounded input signal, for any, the keyword is for any bounded input signal x, there exists a positive finite real number y such that the magnitude of the output doesn't exceed m, real number m, such that the magnitude of the output doesn't exceed m. So this is the condition for a bounded output, right? So if you have a bounded input, the output would have to be bounded as well. If there exists even one bounded input signal that gives an unbounded output, then the system will not be Bible stable. Okay? Right. Now, let's look at an example, some example. I'm going to show that the system T defined by this equation is Bible stable. To show that T is Bible stable, then suppose first that the signal, well, here, let X T be any bounded signal, right? Now, because X is a bounded signal, then there exists a number, a a constant n greater than zero, such that I'm not sure if you can remember the definition of bounded input, bounded signal, right? So if a signal X is bounded signal, then because it is bounded, there has to be a constant n such that the magnitude of X is less than n for all t. Okay. Now we apply X to the system. Okay, so because X is not greater than n, right? So this means that the output y of the output t of, since the absolute value of X is not greater than n, it follows that if you take the square of X, the value from the square will not be greater than n square as well. So that means that the absolute value of the output from X is not greater than n squared, right? So this is a number m. So that means this means that there exists a constant, because n is real, right? That is n. Because there is n, so that is n squared. So there exists a constant m which is equal to n squared, such that the output from t is not greater than m for all t. So the output is also bounded. So up to now we have shown that for any bounded input signal, the output is also bounded, right? So this system is bipolar stable. Okay, so system is bipolar stable. Now another example is the system T defined by this equation. Now we're going to show that this system is bipolar stable as well. So let's start with, let x of t be any bounded signal. Then there is a constant n such that the magnitude of x is not greater than n for all time. All right, now let's now apply x to t. Okay, from the definition of t, the output signal will be t of x equal to k1 of x of t plus k2, right? So we take the absolute value of t here. Now, when we take the absolute value of t here, we're going to have absolute value of k1 x of t plus k2, right? And we know from absolute operator that this is less than or equal to absolute k1x plus absolute k2x, k2. Okay, and this is less than or equal to absolute k1 absolute x plus absolute k2. Actually, this is equal to. But we know that the absolute value of x is not greater than n, right? So this is less than or equal to absolute k1 n plus absolute k2. And we can take this as a number m. So there is m such that the absolute value of the output is not greater than m. Hence, this system is bubble stable, right? For any input, right? For any bounded input, we have shown that the output is also bounded. So the system is bubble stable. Bounded input, bounded output system. Now another system, we're going to show that another system is defined by the equation output is the first derivative of the input. Now we're going to show that it is not bubble stable. Now to show that something is not bubble stable, to show that the system is not bubble stable, then we can again give a counter example to show that a system T is not bubble stable. Okay, we can we can give a counter example of an unbounded input. I'm sorry, of a bounded input of a bounded signal x that gives an unbounded output signal. Okay, to show that something is true, then you have to show for every case, right? But to show that something is not true, you can give a counter example, at least one case that makes it not true. Okay, so now let's get back to our example here. So I'm suspecting that this system is not bubble stable, so I'm gonna give a counter example. So I'm gonna, for this example, I'm gonna give a counter example. I'm gonna let the signal x equal to the unit step signal. There is a jump at time 0. Then we can easily see that the signal x, which is equal to the unit step signal, is bounded, right? X is bounded. The reason why it's bounded, I'll let you think about it. Okay, it's not difficult at all. Now x is bounded, but then uh, t of x would have to be equal to the first derivative of ut, right? And we know that derivative if ut is the delta signal, is the unit impulse signal. Okay, is unbounded because a unit impulse signal is not bounded. It goes to infinity at time 0, since delta t equal to infinity at time 0. So we have found that there is a bounded signal that results in unbounded output, right? So this system, this uh, differentiator is not bibostable. We have shown that there is a bounded input that results in an unbounded output. There is at least one. So hence a differentiator is not bibostable, right? Now let's look at another system here defined by this integral. I'm suspecting that this system is not bibostable as well. So I'm gonna give a counterexample by defining x to be u. So I'm gonna let xt equal to ut. Then it is straightforward to show that x is bounded. But then the output of the system from x is given by the integral from minus infinity to t u of tau d tau, right? And this is t u t. Now this signal is not bounded because you cannot find an upper boundary to this function because t will outgrow whatever you have for the upper boundary. You're gonna find that t will outgrow that upper boundary. There is no upper boundary to this signal. T grows. T always grows, no matter what value, no matter what. See, this is t, right? This is this is a graph. Now, to the plot of t ut is the red line here. It grows indefinitely. It doesn't decrease. It doesn't stay constant. It continues growing indefinitely, without any limit. So this is t of x. This is the output, right? Is equal to t ut. So no matter about upper boundary you put here, your output signal will outgrow it eventually. No matter what upper boundary you put in here, the output signal will outgrow it. So this signal is not bounded. Now we have shown that there is a bounded input that produces an unbounded output. So the system here, this integrable integrator, is not bounded. So an integrator This system is called an integrator because it integrates the input, is not bistable. The reason why this system is called an integrator is because it integrates the input signal. So that's why it's called an integrator. And we have shown that an integrator is not bistable because there is an bounded input that produces in an unbounded output. So it is not stable. Okay. All right. So up to here, I'm not sure if you have any question. Are you still with me, guys? Am I?
Yes.
Okay.
Yes.
All right. Any question? I'm trying to write down everything. Okay. I'm trying to write everything down so that if you don't understand something, you can always go back to the recorded clip, and then you can study for yourselves. All right. But if you have questions, you can always ask now. Okay. You don't have to wait until some time. Right. So I'm gonna move on. So now we have learned a lot of concepts. We have learned how to classify systems. Now, two of the most important properties of systems are linear and time invariant. So this topic will assume that systems are both linear and time invariant. So linear plus time invariant at the same time. Now, a system is called a linear time invariant system, or simply LTI. Whenever I say LTI, it will mean that.
Excuse me,
Yes.
I don't have a new lecture. The unit 6.
Oh, you don't? Oh, okay.
Yes.
Sorry. Wait a second. I'm gonna upload it now. Oh, I think I forgot to upload it. Just a moment. Unit 6, right? Okay. Okay. It's been uploaded. You should be able to see it now. Sorry about that. I forgot. Can you see it now? Go to classroom.
Yes, yes.
Okay, all right. Thank you. Thank you for letting me know. A linear time invariant system is a system that is both linear and time invariant. So the keyword is both. They, it exhibits both of the properties at the same time. It's both linear and time invariant. Okay, right. Now, uh, let's talk about some definitions here. YZS. Okay, YZS. The subscript here is ZS. It is called YZS, and YZS refers to a zero state response of an LTI system. So what is it? What is a zero state response of an LTI system? It is the output signal from the system that is due to the input signal only, with all initial system states set to zero. Now, what are system states? For example, if you're looking at an RC circuit, okay, an RC circuit, a system state of that RC circuit may be the initial voltage across the capacitor. Okay, you have a capacitor, right? And you know that a capacitor is capable of storing charges, and those charges stored in a capacitor will result in the voltage potential difference across that capacitor. So before the input is applied, if you have a voltage across a capacitor that is residual voltage across a capacitor, then that voltage across the capacitor before the input is applied is called the initial state of the system. So the zero state response of an LTI system is the output from that system that is due to the input signal only, all right, and no initial states. We set all the initial states to zero, we apply the input, the output will be called zero state response. So to find YZS, we set all the initial states to zero. We then apply the input signal. Okay, the output from the system will be called the zero state response, or YZS of t. All right. On the other hand, a zero input response is the output signal from the system due to the initial states only. Okay, while the input signal is set to zero. For example, in an RC circuit, if you have a residual voltage across a capacitor, even if you don't apply the input signal, you can still have the output from the circuit, and that output from the circuit is a result from the initial residual voltage across that capacitor. That is called the system state. So the output from an LTI system is a result from two factors. First, the output is a result from the input. Second, the output is a result from the initial states. Okay, so basically you have this. You have a system, right? LTI system. You are applying two things into the LTI system. The first is the input. The second is the initial state. Okay, you're applying the input signal to the LTI. The output is called YZS. You're applying the initial state to the LTI. The output will be called Y0 input. All right. Now, so this is what it means. So to find zero input response, what we do, if we set all the input signal to 0, we set all the input signals to 0. We measure the output signal, okay, that are from only the initial states. The output measured, that is signal, is called the zero input response. The notation is YZI, zero input response. So these are how zero input and zero state responses are defined. Uh, Now, an interesting thing about LTI systems is that the total output from the system is a summation, if the addition, is the combination of the zero state and zero input responses. So if you have a system that has both initial states and input, you can find each one separately, and then you can add them in the end together in the end to find the complete response to that system, from that system. So for example, if you have a uh, suppose you have an LC circuit. Okay, suppose you have an LC circuit. I'm sorry, RC circuit. Suppose you have an RC circuit. This is your system. Okay, this is the input, and this is the output. The output is the voltage across the resistor, and the input is signal X. Now, the potential here is VCT. Now suppose X of t is applied at time t equal to 0, and at t equal to 0, the initial state of the circuit is Vc of 0. Okay, then it can be shown, suppose, well, I'm gonna say that X of t is equal to ut. We are applying the input at time 0, right? We are applying the input to be 1 at time 0. Then it can be shown that the output y is Vc of 0 e to the minus t over rt ut plus 1 minus e to the, well, let's say this is a, e ut. Okay, E is a constant, plus E here, E to the minus, this is RC, T over RC, U of T. Right. So this is called the total output, the complete response. It is a total response. It is a real response. It is a real output from the circuit. Now, this part will be the zero state. I'm sorry, zero input response. Because this part is a function of only the input, the initial state, right? The initial state goes to this term, and this part is called, it is the zero state response. Okay, so if the system here, your RC circuit here is a time linear time invariant LTI system, the complete response is a combination between the zero input response and the zero state response. This is true for an LTI system. You can find your response by finding these two things separately and then add them in the end. You can find you can first find the zero input response by setting the input to zero, and then you measure the output, and the output will be called the zero input response. In this case, the output is given by this expression. Then you take a note of it. Then you assume that the zero state here is zero, and you apply the input at time zero. You measure the output. That output will be your zero state response. Once you have both of them, you add them. Okay, you add them in the end. The result from that addition will be your complete response, will be your response, your output voltage. Either one of these is not the true response. You have to add them to get the true response, the complete response. All right. So this term, this is a result from the initial state only. And this is from the input only. Okay, when we add them together, you're gonna have the true response, the complete response from the system to both the input and the initial state. Okay, we're applying the input and the system has some initial state left over, right? These two together will give you the complete response. Okay, all right. Now, so this is important. This is important. Now it turns out that you can find you can find the zero state response from the system, from an LTI system. It turns out, now suppose L is an LTI system. Okay, it turns out that you can find the zero state response YZS from an input signal xt to an input signal x of t using this integral. Okay, YZS is integrating from minus infinity to infinity, and then x of tau, I'm sorry, L delta L delta x of tau L of delta t minus tau d tau. This integral is very important. It is used to find the zero state response of an LTI system from the input signal x of t. Okay, here I'm writing it down as x of tau, but x of tau and x of t are the same thing. Now, the interesting term inside the integral is this one. So what is it here? Where the term L of delta t, okay, is called the impulse response. It is the output. This is the output from an LTI system. This is the output from an LTI system when first input is the unit impulse signal, and second, all initial states set to 0. Okay, and we have a dedicated symbol for the impulse response of an LTI system. We will almost always call it h of t. Okay, so we reserve the letter small h to be the impulse response of an LTI system. Whenever you see h of t, keep in mind that it is the impulse response to an LTI system. So using this notation, I'm gonna have the zero state response from an LTI system can be found using this integral, integrating from minus infinity to infinity x of tau, and then the impulse response h at time t minus tau, and integrated with respect to tau. Now this integral is very important. It is so important that we give it a name, and we call this integral convolution integral. Okay, the name of this integral is the convolution integral. Integral between two function x of t and h of t. Okay, and there is a symbol for that. We write x of t star h of t. Because the integral here is quite complex, we don't want to write this down every time we refer to the zero state response, right? So we have a shorthand notation for this entire integral. Okay, and that notation, that shorthand notation, is this: x of t, right, is this guy, and then h of this is this guy. So we are writing down x of t and star and h of t. So whenever you see a star, it is a convolution integral. So that this results in the integration from minus infinity to infinity, x of tau h of t minus tau d tau. And if you switch the order between these two, right? If you switch the order, if you put h in front of x, then what you have to do is you're gonna have to switch this order as well. So you have to be careful about the orders here. Okay, if h comes first, then h would have to come first in the integral. If x comes in second, then x here would have to be coming in second in the integral. All right. So now, up till now, we are able to find a zero state response to any particular input, to any input signal x, if we know one thing. Okay, and that thing is the impulse response h. If we know the impulse response of an LTI system, then given any input signal, you can always find the zero state response from that system by performing this integral. Okay, so impulse responses will be our next topic that we have to study. So this is impulse responses. Now, impulse responses, as I said earlier, has a shorthand notation of h of t, and the definition of h is the output is the response of an LTI system from the unit impulse signal with all the initial states of the system set to 0. Now this is important. Okay, you're gonna have to have all the initial states set to 0 to be able to find the impulse responses. Right? If initial states are not set to 0, if there are some initial states that are not 0, then the output, even though the input is the unit impulse, the output will not be the impulse response. For the output to be an impulse response, you're gonna have to satisfy two things. First, the input would have to be the impulse signal. Second, all the initial states of the system would have to be set to 0. If these two are satisfied, then the output is indeed the impulse response. Now, given the impulse response of an LTI system, you can find the zero state response. Remember, the zero state response is a response that is due only to the input signal, not the initial state. Okay, you can find the zero state response from an LTI system by performing this convolution integral. You put the input signal here, and you put the impulse response here, and then you perform the integration. The result from the integration would be your zero state response. Now you may wonder, how do I perform this integral? Okay, you have to have I'll show you how to perform this integral in a moment. Now again, as I said earlier, there's a shorthand notation. Now this integral is quite complex to write down, right, as I said earlier. So there's a shorthand notation. You look at these two, right? There are two functions, x and h. X comes first and h comes in second. So you put x here, which comes in first, and then h, which comes in second here, and you put the star operator here. This star operator, whenever you see it, it means convolution integral. It means this integral. Okay, and the result from this integration would be your zero state response. of an LTI system, of your LTI system having this impulse response. Now let's look at an example. First example is the determination of an impulse response. So suppose we have a linear time invariant system that is defined by this integral. It is an integrator, right? We have seen this earlier. This is called an integrator. This is called an integrator. Now, basically, we're gonna find the impulse response from an integrator. Okay, to find h, right, the impulse response, we set 1 xt equal to the impulse, unit impulse, to all initial states set to 0. Now y of t is equal to integration from minus infinity to t x of tau d tau. So I'm gonna plug in x as delta, right? So this is integration from minus infinity to t delta tau d tau. Okay, and from calculus, right, I can break this down into two parts. The first part is I'm gonna write down integration from 0 to t 0 minus to t delta tau d tau plus y at time 0. Okay, and y at time 0 here, this is actually the initial state. This is the initial state term. And because we want to find the impulse response, right? So we need to set this one to 0, okay? Because here we'll have to set all initial states to 0 to find ht, right? So to find ht, so this is set to 0. And then we remember that this integral is just u, right? This integral is just ut, because this is 1. This is 1 when t is greater than 0. Okay, this integral is 1 when t is greater than or equal to 0, and is greater than 0, and 0 when t is less than 0. And this is just ut, right? This is actually the definition of the unit step signal. So we have it that the impulse response of an integrator here defined here is the unit step signal. So in this example, so h of t is ut. Sorry. Sorry. So in this case, in this example, we have shown that an integrator has the impulse response of ut, okay, here, by performing this, set these two conditions and plug them in to the definition of your system here. I'm not sure if you understand or not, right? But if you have questions, again, feel free to ask anytime, or you can go back to watch a clip later. And if you watch a clip and you have something that you don't understand, you can come up and see me during class. Now let's look at another system. We're gonna find, well, with the above system, we're gonna find this. Okay, we're gonna find the output of that system when the input is ut minus t. So t of ut minus minus capital T, right? So what is it, hen? What is this one? This one is the signal starting from 0, right, and end at time t. Time t, oops, sorry. Time t here, 1, 0. So because the system is linear, I said earlier that we can take t inside of the parentheses. So output, sorry. So as I said earlier, the output of the combination of input is the combination of the output. So we can take t inside by linearity. This is bilinearity, okay? And then from the definition, tu, right? Tu, tu, okay? But, sorry, but t of u is integrating from minus infinity to t u of tau d tau, right? And that we know is t ut. So this term is t of ut. So this is equal to t of ut minus t of ut minus t here. But then this is the input applied sometime later, right? And because the system is type invariant, it means that the output from here has to be the output of this one applied at the same time later. So this because this one is TUT, so this one would have to be T minus T, UT minus T. So this has to be T minus capital T and UT minus capital T because of the time invariance. So the output from this one would have to be TUT minus T minus capital T U of T minus capital T. And this is the answer. Okay, from this example. Right. All right. I think I have to leave here because it's 12 o'clock already. And the next lecture, I'll be seeing you guys in class on Tuesday, next Tuesday. And the code for this lecture to check attendance is Laplace. This is the attendance code. Laplace. All right, Laplace. All right, any questions, guys? Are you still with me? I may be
Yes.
talking a little bit too fast today, but I think we have a clip. I have recorded a clip, so you can go back anytime you like. And when you go back and look at the clip, if there's something that you don't understand, you can come up and see me. Okay? Until next time, see you on Tuesday.
อาจารย์ครับ
Yeah.
อาจารย์จะโพสต์คลิปให้ประมาณเมื่อไหร่ครับ
In the afternoon, because I have to wait for YouTube to process it.
โอ
There's
เค
some
ครับ
time. YouTube takes some time to process it. Once it's done, I can post it.
ได้ครับ
All right. Bye bye. See you next time.
Bye.
See you next Tuesday.
บ๊ายบายครับ
Bye bye.
สวัสดีครับ